Hello everyone. In this lecture, we are continuing with the module 5 of Principles of Communication Engineering for Telecommunication branch, that is pulse modulation. Now, in the pulse modulation, we have already seen what is sampling. So we are just taking a quick revision of that. So sampling is a process of taking periodic samples of the waveform to be transmitted. The more samples that are taken, the more final outcome looks like the original wave. So if you take more number of samples, so the sampled output will look like as a original wave. However, if fewer samples are taken, then other kinds of information could be transmitted. Means the case of aliasing. When the aliasing is there, the information can be different also. Means there will be a loss of information. Means which we want to actually transmit, something else will be received. So now we know sampling process follows sampling theorem, which is called as Nyquist theorem. So it is used to determine minimum sampling rate for any signal so that the signal will be correctly restored at the receiver. So we know that for faithful conversion and reconstruction, the sampling theorem should be satisfied, which says that the original information signal can be reconstructed at the receiver with minimal distortion or without any distortion if the sampling rate in the pulse modulation system is equal to or greater than twice the maximum frequency or maximum information signal frequency. So the sampling frequency by that statement will be Fs is greater than or equal to 2 times Fm. So where Fs is sampling frequency and Fm is the maximum frequency contained of the signal. Now in the sampling we have seen there are three types of sampling. So how the sampling is performed, so we can see that here in the black color it is an analog signal, which is also called as a baseband signal, and then here we are going to have a square pulses which is going to multiply that. Suppose here if you see in this diagram, in the one cycle, suppose if you take from peak to peak, the number of samples are 1, 2, 3 and 4. So here 4 samples are there, means what your Fs is 4 times Fm. So here if you see in the natural sampling, your input waveform is the sinusoidal wave, the sample pulses are there, which is square pulses wave. Now the output waveform will consist of a sample pulses only, but the amplitude will be same as the input waveform. So we can say this is a natural sampling in which the output waveform will consist of the amplitude as same as the input waveform or your modulating signal or your information signal in analog domain. While if you see in the flat top sampling, where your input waveform and same way sample pulses are there, but the output waveform will maintain the amplitude of the sample for the next sample. So we can see here at the starting the amplitude is 0. So we can see here at the starting the amplitude is 0. So that's why that 0 amplitude is maintained to the next sample value. Then at that point sample point is up, so it will go up, then it will maintain to the next sample value, then again it will maintain the next sample, then it will go up like that way. So here in flat top sampling, the output sample will consist of the amplitude will be same as the starting amplitude, then it will maintain for the same amplitude will maintain for the bit duration. So this is a flat top sampling. Now next we will start with we'll go inside for our today's lecture. So that is pulse modulation. So pulse modulation includes many different methods of converting information into pulses. So normally in pulse modulation we're going to convert the information into pulses form, obviously. So that's what is called pulse modulation, into pulses for transferring pulses from a source to destination. Now divided into two categories, so analog pulse modulation and digital pulse modulation. So analog pulse modulation will give rise to in which the output is in analog form, digital pulse modulation in which the output is digital form. So sampling analog information signal. So in pulse modulation we have to sample the analog signal, then converting samples into discrete pulses, we have to convert that into discrete pulses, then transport the pulses over a physical transmission medium, and then transmit it to the physical transmission medium. So normally there are 4 methods. So analog pulse modulation is broadly classified into 3 parts, that is PAM, called as pulse amplitude modulation, PWM pulse width modulation, and PPM, which is pulse position modulation. While the digital pulse modulation will consist of one type, which is PCM, pulse code modulation. So now we will see all the three PAM, PWM, PPM, which is in our syllabus in analog pulse modulation. So in APM, which is analog pulse modulation, the carrier signal is in the form of pulses waveform, and the modulated signal is in where one of the characteristic, and the modulated signal is where one of the characteristic, either amplitude, width, or position is changed according to the modulating audio signal. So here in APM, where we can change amplitude, pulse width, or pulse position of the pulse based on the amplitude of the modulating signal. So based on that, there are three common techniques of APM: pulse amplitude modulation, where amplitude of the pulses is varied with respect to the amplitude of the modulating signal; pulse width modulation, where the width of the pulse is going to vary with respect to the amplitude of modulating signal; and pulse position modulation, in which the position of the pulses will going to, the position means there will be change in the duty cycle. Actually, in the position, the change in duty cycle will be there. So the position is going to vary with respect to the amplitude of modulating signal. So same thing is explained in figure 4.4. We'll see in the next slide. So pulse amplitude modulation. So just now we have discussed the simplest form of pulse modulation. Here the amplitude of constant width, constant position, which is your pulse signal. So its amplitude of having constant width, constant position, pulse carrier is changed according to the amplitude of the modulating signal. So basically the modulating signal is sampled. So we're going to sample by this digital train of pulses, and the process is based upon the sampling theorem. So here, generally speaking, we are going to sample the modulating signal based on the sample pulses, based on the sampling theorem. So here we can see in this diagram, we can see the first figure is modulating signal, then pulses, sampling pulses are there. Now the pulses amplitude is going to change with respect to the modulating signal. We get the PAM. So if you change, if there is shift in the signal, then the second type of, say, third waveform, fourth waveform, we can see it is shifted pulse amplitude modulated signal. Then fifth waveform is a pulse width modulation, where the width of the pulse is going to change with respect to the amplitude of modulated signal, where the amplitude is maximum, width is maximum, where amplitude is minimum, width is minimum, like that, where width is negative, where amplitude is negative, width is more minimum than the actual width of the pulses. And then the last way is the pulse position modulation, where the width will be same, but its position will change, and the position is going to change with respect to the amplitude. Where amplitude is more, width change, position change is more. When the amplitude is less, width pulse position change is less. Then pulse width modulation, the technique of varying the width of the constant amplitude pulse proportional to the amplitude of the modulating signal. So here we are going to change the width of the pulses with respect to the amplitude of modulating signal, also known as a pulse duration modulation, or PDM. Means the duration is going to change, obviously, because we are going to change the width, so on and off time will change. Either the leading edge or trailing edge, or both, may be varied by the modulating signal. So whether leading edge means going up or going down, both can be varied. Means for the positive or negative or zero, can also, anything can be varied both. So pulse width modulation, it has some advantages. So PWM gives better signal to noise performance than PM, because in PM we know that there is variation in amplitude, and the noise mostly affect the amplitude of the signal. So PM is having lesser signal to noise ratio, because the amplitude, the signal is gradually degraded by the noise in the PEM. But while in PWM there is no change in the amplitude, so if there is a sudden change in amplitude taking place, so we can apply to the comparator, and that amplitude variation can be removed, but in the width normally remains same. So pulse modulation gives better signal to noise ratio than the PEM. But the PWM has some disadvantages, that the width is going to change, so obviously the power contained in each pulses will be different. So PWM has advantage when compared with the PPM, that is its pulse are of varying width and therefore for varying power content. So PWM still works if synchronization between transmitter and receiver fails, whereas PPM does not. So in PPM, if there is no synchronization for the bit duration, means for the clock bit duration synchronization is not there, then PPM, pulse position modulation, is not used, while PWM can be used. Pulse position modulation, we will continue with that. So pulse position modulation is when the position of the constant width and constant amplitude pulse within this prescribed time slot is varied. So when the position of the constant width and constant amplitude pulses, means this position is going to change by keeping amplitude and width constant with respect to the amplitude or the modulating signal. So PPM has the advantage of requiring constant transmitter power. So here in PPM we can have a constant power because here we are going to have width same and also the amplitude is same, but in PWM the power transmitter power is going to vary. But the disadvantage of depending on the transmitter's receiver synchronization. But the problem with the PPM is that it requires a proper synchronization at the transmitter and receiver. Otherwise, if no synchronization is also there is mismatch in the synchronization. Obviously, the information regain will be different. PPM has less noise due to amplitude range changes. Also, the noise to signal to noise ratio is good because here again we are keeping the amplitude same because the receive pulse may be clipped at the receiver, thus removing amplitude changes caused by the noise. So here we can say PAM, PWM and PPM vary properly. So modulating signal we can see here PAM the amplitude is changed, PWM the width is going to change of the pulse, and PPM the position is going to change. So in pulse amplitude modulation is which the amplitude of pulses is varied according to the modulating signal. Pulse width modulation is a modulation in which the width of the signal is going to vary according to the modulating signal. Now here if you see here A and B are the two signals. Now A and B are applied to the comparator. If your A is less than B, C is high. If A is greater than B, C is low, and that can be applied to the integrator, and we can get the pulse width modulation output. So comparator and integrator are two circuits which is used to generate the pulse width modulation signal. Modulating B is modulating signal, A is your square pulses or triangular pulses we can say. So pulse position modulation. Pulse position modulation is a modulation in which the temporal position of the pulses is varied according to the modulating signal, amplitude modulating signal. So here in a very clearly way we can see the pulse position modulation. Here the position of the pulses is going to vary with respect to the amplitude. Where amplitude is more, position is more. Position change is more. When amplitude is less, position change is less. So thank you. So in this lecture we have seen that PAM, PWM and PPM. PAM is simple in characteristic, but it has disadvantage of signal to noise ratio is less, and also the power requirement is changing. And while PWM pulse width modulation, it is having better signal to noise ratio compared to PEM and PPM also, but there is a problem is that in every the width duration is changing, so obviously the power transmitted and every pulses will be different, while PPM is having better signal to noise ratio compared to PEM, and also it has advantage that here the power transmitted power is same, but the disadvantage is that in PPM is that it requires a proper synchronization the transmitter and receiver. If there is no synchronization, there will be a problem of receiving reconstruction of the signal. Thank you for hearing.